Welcome to lecture 31 on real-time databases. So let's just introduce many real-time applications, particularly those that are deployed in an embedded context in a real world, actually see a lot of data being generated, right? So their job is to retrieve the data, maybe update internal data structures and process them. So examples would be a network management system, industrial control system, autopilot system. So the main differences are that, of course, the data is different in the sense that the data that is stored in a real-time system, I won't call it a real-time database, but a real-time data store, as opposed to a traditional database, is that you're sensing data from the environment. Every datum has a timestamp, and it's possible that after the timestamp, after a certain delay, the data itself may expire. So these are like small chunks of data with a time and a validity. So a traditional database system doesn't really have those constraints or those requirements, but in this case, we actually do have that, right? And also, performance is an important issue. Plus, if data stores are there on embedded devices, the devices themselves have limited capabilities, right? So, if we consider the temporal nature of data, that is by far the most important consideration in a real time setting, that after the elapse of a pre-specified time, the data doesn't remain valid anymore. So consider periodic data that is generated by a temperature sensor. So as and when new temperature readings become available, the old data becomes stale and obsolete. Other examples of temporal data, stock market price quotations, right? So as new prices come in, as the value of a share gets changed or updated, the old values, old quotes become obsolete. Again, fly-by-wire aircraft. So a typical aircraft, lot of sensors are mounted, right? So every few milliseconds, the controller would receive the current altitude, velocity, acceleration, etc. So now the point is that if, let's say, a decision has to be taken based on the instantaneous values, then older values beyond a few milliseconds, right, in the past, lose their value entirely. So if I were to continue this example, from the received data, you would want to, let's say, compute the position, compute the deviation from the ideal position. So all of these things are only possible with recent data, not with old data. So that's the reason, even if we want to process it or store it, we have to do all of that within real time bounds. The moment a deadline is missed, the data loses its validity, either in total or partially. So such data is dynamic, reflects the state of the environment, such as sensor data. It could also be derived data that you derive from other parameters, like in a computer derivative or something. And again, after processing, it is given to actual actuators, let's say in a chemical plant, to control the rate of chemical infusion and so on. The static data, on the other hand, is fixed configuration data, which is collected and stored. So again, in the real-time systems may need to access a lot of static data, and that too has to be done quickly. It is also possible that a given algorithm may require some dynamic data generated by a dynamic data source and some static data generated by a static data source. So both of them have to follow real-time requirements. They can't take a lot of time. So how do you represent temporal data with a three tuple? The value is, of course, the value of the data. AVI is the validity interval, the absolute validity interval, and TM is the timestamp at which it was collected. Examples, let's say the value 120, valid for 5 milliseconds, collected at 100 milliseconds. So its validity in this case is between 100 and 105, right? So the other characteristics are that the moment you set up a system in an environment, you have an environment and a controller, and of course an actuator. You have a real-time data management store. And there has to be a notion of consistency which is different from traditional database consistency, in the sense it has to be temporally consistent. So what does that really mean? So what means that all the data that is stored has to satisfy our validity constraints, right? So all our validity constraints, instead of expressed as this term AVI, have to hold. So the two main requirements are absolute validity and relative consistency. Let's see what they mean. Absolute validity is with respect to external time, in the sense that if I've read the environment at, let's say, t equal to t0, the data that I'm seeing is within t0 plus AVI, right? So my current time is basically is in between t0 and t0 plus AVI, which means the data is valid. Relative consistency basically means that if I'm looking at a bunch of data, right, not just one value but 20 values, all 20 values are valid and they all correspond to the same system state. In the sense, it makes little sense to look at today's pressure with yesterday's temperature. If you're looking at pressure and temperature, they have to be collected at exactly the same time instant. So if I were to look at relative consistency for a derived data item to be correct, all the data items have to be relatively consistent with each other. For example, in an anti-missile system, if I'm using the velocity and position, then they have to correspond to each other at the same instant of time. Or maybe a little bit of deviation is acceptable, but not a lot. You can't use let's say the position of an earlier period with the current velocity. That will give you an erroneous result. So what does relative consistency ensure? That contemporary data items are used to derive new data and all the data items are consistent with each other, right? Relatively consistent with each other. So we define a relative validity interval called RRVI. So the condition for absolute validity would be like this, that any data item D is considered absolutely valid if the current time minus the timestamp at which the data item was collected is less than the validity interval of that data, right? So this is obvious. We have been seeing this in many forms. For relative consistency, on the other hand, we don't look at one data item, but we look at a bunch of data items, right? So a set R of data items is said to be relatively consistent if and only if for any two data items D and D dash, I look at their timestamps of when they were collected, right? I'll compute the modulus or the absolute value of the difference of their timestamps, and this needs to be less than a given relative validity interval threshold. If this is indeed the case, then it means that all the data items have more or less been collected in the same time interval, roughly, right? This is something that we can say. And if we can say that, we can say that all of them are relatively consistent. Example of a real-time database process controller. Data and controller configuration, in this case, of course, everything has to be in sync, which is what relative consistency measures. But the other thing is the data volume. So we could have megabytes of information, right? A lot of information. And if we need a response within few milliseconds, we'll have to go through all of that data, which means we need very fast data structures, and also ensure that our scheduling algorithm, etc., is all in line with this, in the sense it can actually provide, this level of a response, this millisecond level of response, right? Even under worst case situations. Like a spacecraft control system, it will maintain contact with the ground controller using a bunch of things, antennae, receiver, transmitters, and so on. And the sensor data will be sent. So, of course, we ensure relative consistency, right, to monitor the health of the spacecraft and to also compute tracking information. And to furthermore, to ensure that we are getting the correct data, which is consistent both from an absolute and relative perspective, we may want to add some degree of redundancy, which means additional components that don't do much. Only thing is they enhance the reliability of the system. This does, however, increase the volume of data in the sense that if we have, let's say, two pairs of sensors or two sets of sensors, it'll double the data, you'll have to deal with it. But again, that's the price you pay for reliability. So there is a trade off, right? More reliable is the system, more is the data, the harder it is to ensure real time correctness. So now let's look at a few database concepts, right, for those who don't have a background, and we will then relate them with real time concepts. So ideally speaking, you have multiple parallel threads accessing a database. Each one of them does reads and writes. So how do you ensure correctness, right? How do you ensure that reads are reading what they are supposed to read? Or looking at it another way, at any instantaneous point of time, if I look at a database, it appears to be in a consistent state. Consistent basically meaning that it satisfies our intuitive notions of correctness. And many databases also define what is consistent. Consistent means consistent with specifications, right? Which basically means it's correct. Because anything that is consistent with specifications is deemed to be correct. The moment we have concurrent transactions, they could be interleaved. So the aim is to, of course, increase the throughput and resource utilization. So that's the reason we will ideally want to maximize the number of concurrent transactions in any database system. So a database schedule will be a sequencing of the actions of various concurrent transactions. In the sense, one transaction would be reading, other one would be writing, another one will be reading, writing, etc. Because of the concurrent nature of transactions, some database schedules can actually produce erroneous outcomes, or let's say violate the consistency and integrity of the database, in the sense take it to a state which many human observers will say it's not correct. So given the fact that databases has a separate course and so on, I don't really want to take you into it. But what I would like to say is that the database literature has a lot of this described, so you can look at it. So the key point is that there will be a certain violation of integrity, which is not something that you want, in the sense that the simplest example that is given is something like a data race, where given an account, you just want to increment the balance, right? So let's say the variable account, or let's say account dot balance, you just want to increment it by one. So what two transactions can do is that if the account balance is 100, one transaction will read the value as 100, the other one will read it as 100. Both will internally increment it to 1, save it in a temporary variable, and finally write it to the database. So the final value will be 1, which is incorrect. The final value should actually be 102. But the reason is that because allow, we didn't create some degree of synchronization between them, they were able to write an incorrect value, which has destroyed the integrity of the value account.balance. So, in a sense, the database now is in an incorrect or inconsistent state. That is why the moment we have concurrently executing transactions that access the same values or variables, or row entries in tables, we have to somehow limit them, constrain them, restrict them, such that such erroneous outcomes are not produced. Databases definitely do a good job in restricting concurrent executions. So they have concurrency control protocols which precisely do what I said, that the moment they detect the same variable is being accessed, they let one transaction finish before allowing the other one to begin. So the concurrency control protocols are important. So before discussing that, let us discuss the ACID properties in a database. The first ACID property is atomicity, which says that in a transaction, either all of it is done or none of it is done, right? So either all of it appears, say if let's say transaction has multiple reads and writes and so on, database updates, either the entire transaction is done or it appears as if it has not started. Consistency means at all points of time, the database appears to be the contents appear to be correct. Isolation means that if there are two transactions that are executing concurrently, they do not interfere with each other and they never see each other's partially written state. So let's say if a transaction is writing to five, let's say variables or five rows within a table, you never see a half state where three rows have been updated and two more have not been updated. So that is not seen. And finally, durability, which is that the moment a transaction finishes, so this action is known as a commit, it becomes permanent in the database in the sense after that, if there is a systems crash, the data still remains. So, how is atomicity maintained? While each transaction preserves consistency of the database, it is possible that because of the example that we showed with account.balance, because of the integrity of the database, one is failing, right? One transaction has to fail. Fail means it has to be killed. So, because we saw this example, right? Both read the balance to be 100, both internally increment it, and both write this value. So, the final value is 101, and which is incorrect. But if let's say we kill one transaction, then this path is correct. So, it is important that if let's say both the transactions conflict, what does it mean? That they access the same location and one of the accesses is a write, right? So, they access the same location at roughly the same time without any ordering between the transactions. And one of the accesses is a write, so that's a conflict. The moment there is a conflicting access to the same location, one of the transactions has to be completely killed. This is known as a transaction failure or aborting the transaction. So, aborting the transaction means you'll have to roll back all of its changes because it could have written to other variables also. So, roll them back. Roll them back basically means replace the contents of those locations with earlier values. So, coming to cascaded rollback, a transaction might need to be rolled back and restarted. Because it had read a value that was produced by, let's say, some other transaction, and that other transaction got aborted. Or maybe it was in a conflicting situation. And in the case that we showed with account.balance where one had to be killed. So we'll use the word aborted from here on. So rollbacks, of course, have serious implications for real-time applications. Because assume a real-time transaction, right? It goes on. Long time later, one transaction is rolled back, and because some other transaction had written data written by it, that is rolled back, so on and so forth. So these transactions could miss their deadlines because of this delay of rolling back. So this can all be achieved by ensuring that every transaction reads only data values written by committed transactions. If that is the case, then we will not have this cascaded aborts of one transaction aborting. So mind you, a committed transaction can never abort. It has committed. But all other transactions that are alive can abort. And as I have shown, we can have cascaded aborts in the sense one transaction aborts. Because it had read something that T2 read, that also aborts. Then T3 aborts, so on and so forth. So if you disallow this behavior in the sense if you say that every transaction will only read whatever has been written by committed transactions, then cascading aborts will not happen. The last is the durability property that once a transaction commits, of course it cannot be aborted, but we also want all of its changes to be written into permanent storage, which is let's say the hard disk. So that can be ensured. And once a transaction is committed, it will not be a part of any abort sequence, including a cascading abort sequence. So, what are the fundamental differences between task scheduling and transaction scheduling? So, CPU is a serially reusable resource, so multiple processes cannot be running on a single CPU at the same point of time. But in resource sharing algorithms, we are potentially looking at too many data items, right? It's, in this case of a CPU is a single CPU, but here the number of data items or the number of memory locations or number of table rows is very, very high. As a result, the same algorithms will not scale. And also the other idea is that transactions are or could be quite long. So the different concurrency control schemes that have been designed to ensure that transactions do not interfere is basically by the serializability correctness property, where it says that the final result, whatever is the final result that you see, or for that matter any intermediate state as well, is equivalent to some serial schedule, serial execution of these transactions. In the sense, it could be T1 first, and then T5, and then T6, and so on. Sorry, T5, and then T6, and then T7, and so on. But it's equivalent to some serial schedule. So if you see our account.balance example, where we had two transactions, both were reading the value 100, and then both were writing the value 101 to the final balance, this is not equivalent to a serial schedule, because if T1 executes first and then T2, the final balance is 102. Similarly, if T2 executes first and then T1, the final balance is still 102. So regardless of however you do it, it is not equivalent to a serial schedule. As a result, this output of 101 is wrong because it does not satisfy serializability, which is by far the most popular correctness criteria in databases. So if I were to look at concurrency control protocols, you would want to ensure serializability. You would want to ensure some degree of priority inheritance. You would want to ensure no deadlocks, and you would want to ensure guaranteed time bound completion. So there are two methods broadly that are used. The first are optimistic protocols, and the second are pessimistic protocols. So in optimistic protocols, what happens is that you allow all transactions to progress. Just allow them to progress without any restrictions. And then you prune or you kill some of the transactions. Okay. So in this case, what happens is that you just allow things to proceed. The moment there is a problem, then you take some corrective action. Pessimistic protocols are, you disallow certain types of transactions from progressing, in the sense it's some sort of a rate control for transactions, where if you feel that there is a chance of a conflict and there is a high chance of a transaction getting aborted, you don't launch it in the first place. So pessimistic protocols are mainly used before a transaction can perform any operation on a database object. So what you do is you basically check. If you feel that there is a risk, you take appropriate action. So what you do is that in a pessimistic protocol, before you do anything, you explicitly seek for permission. In the sense, you run a small algorithm which checks if there will be problems or not. Right? Problems, what kind of problems? Conflicts. Then what you do is you go ahead and you lock the necessary data and you perform the necessary changes. So here it is important to discuss the two-phase locking protocol, which is by far the most important locking protocol for concurrent transactions. It is also guaranteed to be deadlock free. So the key point, of course, is guaranteed to be deadlock free as long as locks are acquired in a certain global order. If you don't acquire locks in a certain order, then of course you can have deadlocks. The execution of any transaction proceeds in two phases. You grow the phase, in the sense you acquire all the locks, and then you have a shrinking phase where the locks are released. So in this case, what happens is that you first acquire all the locks, then you do the processing, right? And then you release the locks. So once a lock is released by a transaction, its shrinking phase starts. In a sense, you just have two phases. One is the acquire phase, where you just go acquire, 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 acquire. And once the processing is done, then you reduce the number of locks, which is known as the shrinking phase. So at this point of time, no further locks can be acquired by the transaction. So conventional 2PL is unsatisfactory. Well, the reason is that you can have priority inversions in the sense that a low priority task could hold on to a lock and could hold on to a lock for a very long time, which means a high priority task could just wait there. And I wouldn't say starve, but it's basically undergo inversions. There'll be long blocking delays. Then, you are not considering priorities and so on. So, as I have said, if you acquire resources in a given global order, you'll not have deadlocks. But in a general two-phase locking scheme, the slides are correct. You will have deadlocks, right? But again, it's possible to slightly modify it. If you know the set of all the locks that you will acquire, you just acquire them in a certain global order. So, of course, priority inversion is a problem with two-phase locking. So, it's possible for a low priority transaction to hold a lock on a data item and for a high priority transaction to wait. Because transactions are usually very long, the low priority transaction may wait for a very long time. Sorry, the high priority transaction may wait for a very long time. So, to limit this delay, we can have a variation of this protocol, 2PLWP, where the priority of one task TR is more than the priority of one task TH. Then what happens? So, then what happens is that TR waits, but there is priority inheritance in the sense the priority of the task TH is increased to that of the priority of task TR if so in this case, there is priority inversion, right? So the priority of TR is more than the priority of TH. So this is basically 2PL with priority inheritance, two phase locking with priority inheritance. So unlike a pure priority inheritance scheme, this is applied only when the higher priority transaction is aborted while it is blocked. So basically what happens is that if the higher priority transaction while it is blocked, it gets aborted because of conflicting accesses, then the inheritance is applied and the elevated priority task will retain its priority until it terminates. Of course, this could lead to undesirable situations in the sense that it could effectively block other tasks, right? So, this is undesirable. But anyway, this is the scheme. So, the 2PLWP scheme, if I would just go back to the previous one, it is two phase locking with priority inheritance, but there is a catch. The catch is that you don't inherit the priority all the time. You inherit the priority only when the higher priority transaction is for some reason not able to complete, which basically means that it is going to come back once again, right? If it got aborted, it means that it's going to come back once again, it's going to have higher priority then. So it's much better if we finish the execution of the current task. And how do we finish it as soon as possible? With priority inheritance. But of course, as we have seen with the HLP protocol in CPUs, unnecessarily jacking up the priority can lead to problematic behaviors. Particularly, many other tasks can get blocked. So, that is an issue. So, under high load, what will happen is that most transactions in the system will get jacked up to a very high priority. And then it would as if be that everybody has the same high priority. So, the performance would reduce. Under a low load situation, 2PLWP is expected to perform better because of the fact that anything that ever impedes a high priority task, if we bump up its priority, then it will ultimately end up benefiting the higher priority task. So instead of 2PLWP, let's have 2PLHP, which is another protocol. It, to a certain extent, ameliorates the problems of 2PLWP. So let's assume that a transaction is requesting for a lock which is held by a lower priority transaction. This is the classical priority inversion scenario. The lock holding lower priority transaction in this case is aborted. So in this case, the moment a high priority task comes, the low priority task is simply aborted. So what happens? So if there is no conflict, then TR accesses the data item. Otherwise, if a high priority task is waiting on a low priority task, the low priority task is aborted. Otherwise, else TR will wait for the lock as is the normal situation. So this is the normal situation. In the previous situation, again, there was a priority inheritance, right, in subject to certain conditions. So in this case, what you do is you straightforward just kill the low priority task. So let us now describe the 2PL HP protocol. So this does outperform both 2PL and 2PL WP, which appears unexpected. So what happens is that the 2PL under 2PL HP, whenever a transaction aborts, of course, work is wasted. So this is what we have argued in the previous slide as well, that this is what leads to wasted work, useless work. And of course, this does happen whenever a high priority task will require a resource locked by a lower priority transaction. But what will happen is that it was found to be a better idea to kind of allow a high priority task to execute immediately, kind of similar to a preemptive CPU schedule, even if we have to pay the price of losing work which a low priority task had done. So, again, this would depend on the workload. It's by no means a general statement which can be proven, but it has definitely been observed in many practical scenarios that 2PL HP is performs better than 2PL and 2PL WP. So, pretty much if all the transactions are dependent on a single resource, they will undergo serial execution one after the other rather than something which is serializable, because serializable basically means that they are executing concurrently, but the effect is as if they are executing one after the other. But in this case, they're actually executing one after the other. So for high priority transactions, 2PL or 2PL WP for that instance are clearly worse algorithms than 2PL HP, which kind of gives a high priority transaction immediate access. So looking at optimistic protocols where you allow transactions to freely access any data that they require without checks, at the end of a transaction, which is when a transaction is close to being committed, a validation test is conducted to see if we should commit the transaction or not. This basically means that we verify all the accesses that this transaction has made, other transactions have made, and basically look at committed transactions, including the transactions that we are about to commit, right? And see if we can create a serializable schedule, which means it would appear to any external observer that the transactions have been executing one after the other, even though internally that has not been the case. So in forward OCC, OCC stands for optimal concurrency control. Transactions read and update data items freely, but they store their updates in a private region. They don't make it public. This is because of the isolation guarantee. Updates are made public only at transaction commit time. Before a transaction is allowed to commit, it needs to pass a validation test. What does the validation test do? It checks if there is a conflict between the transaction that is being validated and all other transactions that have committed. If there is no conflict, then everything is fine. If a conflict is detected, the transaction is aborted. So this will guarantee the atomicity and the durability properties. There is a notion of OCC sacrifice which explicitly considers the priorities of transactions. It introduces the idea of a conflict set, where the conflict set is defined as all the currently running transactions that conflict with the validating transaction, right? So any transaction that is validating, you look at all the currently running transactions and you basically measure the number of conflicts. So the moment a transaction reaches the validation stage, you check for conflicts with all the currently executing transactions. If conflicts are detected and one or more transactions ends up having a higher priority, then the validating transaction is aborted right then and there. So again, this is an idea that takes the traditional optimistic concurrency control algorithm, the classical algorithm, and introduces a notion of real-time execution into it by bringing in priorities. So what you do is before you commit, you check your conflict set. You look at your priority and the priority of the transactions you're conflicting with. Even if there is one transaction which has a priority greater than yours, you abort. Right? Otherwise, what you will do, if that is not the case, if you end up having the highest priority, then in any case, the rest of the transactions cannot commit because they conflict with you. So you commit, but all the other transactions in the conflict set are aborted and restarted. So OCC sacrifice is one of the better protocols. So the two-phase locking and so on, these were all pessimistic protocols, right? So in pessimistic protocols, you basically don't allow bad things to happen, and so you basically, before doing an access or other things, you kind of do things a priori. But 2PL was worse than 2PL WP, and it was found to be empirically worse than 2PL HP. But again, these were pessimistic. In the world of optimistic concurrency control, OCC sacrifice is one of the better performing protocols. So it is possible that a transaction is sacrificed because of some other transaction that is sacrificed later and so on, which could lead to wasted computations, ultimately leading to a deadline miss. Here is what you can do, that when a transaction commits, it will notify all the running transactions. Each running transaction will check if it has any conflicts with the committing transaction. If any conflicts are detected, then the transaction carrying out the check will immediately abort and restart. So here also the idea is quite similar, that any committed transaction need not check conflicts with already committed transactions, because when they committed, they would have done a check, right? And a conflict is a commutative operation, right? So in OCC BC, what happens is that once a transaction reaches its validation stage, it is guaranteed commitment. So this is kind of making the regular optimistic concurrency control mechanism slightly more pessimistic by adding this broadcast angle, right? So we have looked at two OCC protocols. One is OCC sacrifice and the other is OCC BC. In OCC sacrifice, our logic was that, look, we are sacrificing one transaction because of another one. So there is a possibility of a cascade, right? So if you go back to this slide over here, this is what was our argument, that a transaction may be sacrificed because of some other transaction that is sacrificed later and so on. So that's why we said that the moment you do it, you just broadcast it to everybody, right? Because what can happen is that in consider the OCC sacrifice protocol. So we have a validating transaction and we have another transaction T1. So the T1 transaction may have a higher priority. So what will happen is that we will sacrifice V in favor of T1. But then it is possible that another transaction T2 will, at this moment, maybe it doesn't have a conflict with T1, but then it will make some access which will have a conflict. And T2 may enter the validation stage, and because T2 has a higher priority, T1 will get sacrificed. So this process can continue, right? So because this process can continue, OCC sacrifice can lead to a cascading set of sacrifices. To stop this, we have another protocol known as OCC BC or OCC broadcast commit, which says that what you do is that when you are committing, you notify just all the running transactions, and you check with conflicts. If any conflicts are detected, then the transaction carrying out the check will immediately abort itself and restart, right? So here the idea is that because you are doing that, because you are broadcasting, the moment you reach the validation phase, it is guaranteed you don't have any conflicts with anybody. So you are guaranteed commitment, right? So, mind you, previously in OCC sacrifice, because you were in the validation phase, it did not really guarantee that you will not be sacrificed, right? You will not be aborted. But in this case, once you reach the validation stage, you are guaranteed to commit. So, what happens is under low load situations, most transactions are successfully validated. Under heavy load conditions, a large number of transactions will fail. This will lead to a severe reduction in the throughput and increase in deadline misses. That is why performance of OCC protocols will show a drop. So similar to, if you would go back to our discussion on real-time communication, the same way we had compared A0 2.4 and A0 2.5. Here, if you see the load, with low load, OCC is always better because there's no reason for doing any check. Either use OCC BC or OCC sacrifice and go forward. Pessimistic protocols don't do well for low load, but in a high load scenario, they do much better, mainly because you do the checks and you reduce the amount of wasted work and aborts. So, coming to a conclusion, this ensures that high priority tasks meet their deadlines. Real time databases, of course, have to use appropriate concurrency control protocols. The main categories are optimistic and pessimistic. So, we saw that in a low load scenario, optimistic protocols do substantially better than pessimistic protocols. So, this completes the lecture on real time databases.